Professor, can you hear me?
Yes, can you hear me okay?
Audio. Professor, can you hear me?
Yeah, can you hear me all right?
Yes, now I can.
Perfect. All right. Well, let's get rolling then. So good morning, everybody. I hope you're doing well. So today we are just continuing our journey through chapter 3. And again, in chapter 3, we are learning about different formulas to take derivatives so that we don't have to approximate at points like we were doing in chapter 2. So having these formulas is going to help us answer a lot of questions about the function and the behavior and do all sorts of analysis. But before we can do all those applications, we need to learn all these derivatives. So last time we learned the power rule, right, where we took the power, we subtracted 1 from the power, and we also looked at sine and cosine. And today we are going to be learning about derivatives of exponential functions and the natural logarithm. So that's our plan for today. So I'm going to go ahead and turn on the dot cam here. Okay. So we are just adding on to our list of formulas. We will need to know all of these and how to apply them. And again, I just want to emphasize that one of the key factors in really understanding these formulas is being able to look at a function and identify what type of function it is so we know what type of formula to use. Okay, so today we're going to be talking about exponential functions. And so consider the function f of x equals 3 to the x. Okay, before, if we wanted to approximate the derivative at a point, we would be doing the average rate of change near that point. So we would be using values like, f of 0.1 minus f of 0 over 0.1 minus 0, right, to approximate the derivative at a point. And so we are not going to be doing that as part of what we're doing today. This is more to showcase the fact that if we were to do this for every point for 3 to the x, if we were to approximate the derivative at 0, and then approximate the derivative at 1, and then approximate the derivative at 2, so on and so forth, and we were to draw those, this is what the graph is going to look like. Okay, so the black line is the function 3 to the x, and the red line, which is super close to it, is the derivative. So what I want you to notice is that these have the same shape and they are very, very close in what they look like, right? So that's interesting. And so what mathematicians did is they did this for a whole bunch of exponential functions to figure out what a pattern might be for all types of exponential functions. If we look at the same thing for 2 to the x, 2 to the x is this black line, and then the derivative at every point is this red line. So we see that it has the same general shape, but it's not quite the same. So what we get from this is that the derivative is some form of exponential function, right? Because they have the same sort of growth pattern, but it's a slightly different exponential function. It looks like it's been multiplied by something, right, to make it slightly different. And so again, if you look at enough of these, right, over time, you start to notice some patterns. And it turns out that there is a pattern for exponentials and that we can use that pattern to then come up with our formula. So if we have a function f of x equals a to the x, it turns out that the derivative of a to the x is going to be a to the x, so the same exact thing back, times the natural log of the base. Okay, so the base is the number that's down here in the function. So what's a quick example of that? So let's say we have f of x equals 3 to the x. That's the one we saw the picture of. Using this formula, our derivative would be 3 to the x, the same thing back, times the natural log of the base. So we get this same function back, which makes sense because when we looked at those pictures, they were very similar. But now we multiply by a factor that is related to the function, right, by this natural log. And so this will be true for any exponential function. So within that, we have two sort of special cases of exponential functions that are really interesting. And so we look at them separately, and then we sort of have derivatives that are using this, but we can write separately because they're a special case. So what does that mean? So let's consider the case of e to the x. Okay, so e to the x is an exponential function where e is the base, e is a number, it's approximately 2.71. And so if we were to apply this formula, right up here, this exponential formula, we would get e to the x times the natural log of the base. So we can absolutely do that. We apply the formula just as it is. However, the natural log of e is 1, right? So the natural log and e are related reciprocal functions. And so since this is 1, anything times 1 is just itself, which means that the derivative of e to the x is just e to the x. So that's a special case, and we use the formula to see why that's true, and it's because this particular value is 1. The natural log of other numbers is not 1, so we don't get this sort of nice simplification, okay? So that's our first sort of special case. The second special case is related, and we have to do a little sort of algebra magic to make this work. So let's say we have a number up in the power. So e to the 2x, e to the 5x, e to the 7x, okay? Well, algebraically, we can rewrite this function. So I'm not taking the derivative yet. I'm just talking about doing a rewrite. And I can write this as e to that constant raised to the x. I can separate the c and the x by making it e to the c raised to the x, because if you have a power to a power, you multiply them together. So you can also separate them that way. So when we take the derivative and we apply our rule, my base now, I'll do this in red, my base is e to the c, right? Because that's a number, because e is a number and c is a number. So e to the c is a number. So the rule says I get the same thing back. So e to the c to the x times the natural log of the base. But my base here is e to the c. And so what's interesting here and what ends up happening is that we can rewrite the first term as e to the cx again. And now if you take the natural log of something raised to a power, that power can come down out front. So we get c ln e. And then the same as last time, we know that the ln of e is just 1. And so that can go away because anything times 1 is itself, which means that the derivative of e to the cx, where c is any number, is e to the cx times c. So that c comes out, okay? So these are two special cases. They're both related to e's. If your base is not e, you're going to default to the regular formula. If you have e to the x, the derivative is e to the x. If you have e to the cx, the derivative is e to the cx times c. One thing that I want you to notice here is that the power does not change. So when we had up here 3 to the x, this was still 3 to the x. It was not 3 to the x minus 1, right? Subtracting 1 from the power is only for the power rule. The power does not change when we're dealing with exponential functions, okay? So very quickly, just as sort of a demonstrated example of the second property, let's say f of x equals e to the 4x. So I have a number up in the power. My special case number 2 rule says I'm going to get the same thing back, e to the 4x. I always start by starting with the same thing. times whatever that number is. So it'll be times 4. You can write the 4 afterwards. You can write it before. You can write it as 4e to the 4x, but that 4 has to be part of your derivative. Okay, so now we're going to practice just these 4 examples here of some exponential functions where you're going to apply this rule here to make sure that we can get it written out. So I want you to take about 2 minutes and sketch out the derivative for each a, b, c, and d. Just as a reminder, pi is like e, it's also just a number. However, the natural log of pi is not something special, so you do just have to apply the rule regularly. Okay, so take about 2 minutes, sketch out the derivative of each of these functions, and then we'll go through them together. All right, take about 30 more seconds. All right, so let's go through these. So again, we're just applying this rule and making sure we get comfortable with writing it out and recognizing exponential functions. So here we have 7 to the x. So I notice it's exponential because the variable is in the power. And so I use my exponential rule, which says I get the same thing back, which is 7 to the x, times the natural log of the base. So times natural log of 7. Okay, it's really easy for students to not be super careful and write natural log of x here, and that's not the same thing. It's the natural log of the base, so it has to be whatever this number here is. Okay, let's look at the second one. So the second one is e to the x. That's one of our special cases, and we said the derivative of e to the x is e to the x. Okay, typically we do not write the times ln e because again, ln of e is just 1. For part C, I have 1.2 to the x. Again, my variable is in the power. So I get 1.2 to the x back. I get the same thing. Nothing changes. I'm not subtracting 1 from the power or doing anything to that. I'm simply multiplying this by the natural log of the base. And my base here is 1.2. And then finally, pi to the x. My derivative here is going to be the same thing back times the natural log of the base. And my base here is pi. So here I have pi to the x times ln pi. So that's just a little bit of practice on that first rule. We're going to add one more rule to this, which is the natural log of x. And so again, the way we figure out what the derivative is through patterns. So mathematicians use the average rate of change to approximate the derivative at 1, at 2, at 3, at 4, and then look for a pattern. And what we discovered is that if your function is the natural log of x, the derivative of the ln x is 1 over x. So whenever you see the natural log of x and you have to take the derivative, you get 1 over x. And I want to make sure that we're really clear that the natural log of x is different than something like the natural log of 7. If there's a number in here, then it's a constant, okay? And that's important because if your function is ln x, the derivative is 1 over x. If your function is, say, the natural log of 7, right? Say we started with that for some reason, the derivative of that is 0 because ln of 7 is a constant, it's a number. Okay, so make sure that there's that variable in there when you're taking the derivative. Okay, so now we have a bunch more rules to add on to what we looked at last time. So these are all the rules we have so far. If you have a constant, the derivative is 0. If you have a linear term, the derivative is the slope. If you have a power function, you use the power rule where the power comes down and x is in the base here. Derivative of sine is cosine, derivative of cosine is negative sine. Now we have a to the x, the derivative is a to the x ln a, derivative of e to the x is e to the x, and the derivative of the natural log of x is 1 over x. So as we keep adding on these rules, it's a good idea to sort of keep track of them in general so that you have them for reference. Now, just like last time with the power rule, the constant multiple rule, so if you have a number in front, that holds true for exponentials, so that number is going to multiply the derivative. The sums and differences rule, so if you add or subtract terms that have exponential or logarithms, you can still just go term by term. And the second derivative process, so if we wanted to get the second derivative of an exponential, we would apply the rule 2 times, right? Those all apply to the types of functions we've just added, right? To the exponential and logarithmic types of functions. So we're going to go ahead and sort of practice with all these rules put in place. And hopefully you remember how we applied these last time. But we're going to do example 2 here. And we're going to be looking at, cover this up so we don't get too confused here. We're just doing A through D. We want to look at each one and find the derivative of each function. So again, you can go term by term, right, to take the derivative. When you have a constant in front, like 2, that 2 has to multiply the derivative of 3 to the x, that constant multiple rule. So I want you to go ahead and try this out now that we've sort of added in those other things we talked about last time. Take 2-3 minutes, see if you can figure out the derivative for each of these functions, and then we'll go through it together. take about 30 more seconds. All right, so let's go through these. So for the first one, if we go term by term, the first term is 5 to the x. This is our new rule. It says we're going to get the same thing back, 5 to the x, times the natural log of the base. So that's our first term, minus, now we take the derivative of the natural log, which is 1 over x, plus, now we take the derivative of 2 times 3 to the x. So that 2 is going to multiply the derivative of 3 to the x, and the derivative of 3 to the x is 3 to the x times the natural log of 3. Okay, so don't leave that 2 off because it's multiplied by the function. It's the constant multiple rule, and it comes with us to the derivative. So that's how we write that derivative of part A. For part B, again, we go term by term. The derivative of e to the x is e to the x. The derivative of 3 ln x, well, again, that 3 is going to multiply the derivative of the natural log, and the derivative of the natural log is 1 over x. So we can write it like this, but we could also write the second term as 3 over x, right? So 3 times 1 over x, you can put that 3 into the numerator. So either of these is fine, okay? For part C, we go term by term. The first term is 10 to the x. So the derivative is 10 to the x ln 10 plus the second term, we have 5 ln x. So we have 5 times the derivative of ln x, which is 1 over x. And again, if you want to write that as 5 over x, that's totally fine. For part D, f prime of x, we have e to the x as our first term. The derivative of e to the x is e to the x plus, now the derivative of 6 to the x is 6 to the x ln 6, so times the natural log of the base, minus, now the derivative of the natural log is 1 over x. Okay, so again, we're going term by term as we go through, separated by addition and subtraction. If there's a constant out front, like there was in these cases, that constant has to multiply the derivative. So this example used the constant multiple rule as well as the addition and subtraction. The next example, okay, we're going to look at, it's going to help us understand 2 things. So we're looking for the first derivative of this function and then the first derivative at 1. So again, as a reminder, when we find the derivative function, it's because that will allow us to find the slope of the tangent line at any point. So we are interested in finding the slope of the tangent line at 1, okay? And so when we do this, it says give an exact answer. So what that means is that we should not be turning anything into decimals, right? So say you have something like e to the x and you plug in a 1, you are going to leave it as e to the 1, because if you turn that into a decimal, it is no longer exact, it becomes an approximation. So when you plug in 1 for the first derivative and the second derivative, you do not want to turn anything into a decimal. You're going to leave it in the form that it's in, okay? So you're going to find the first derivative of this function and then plug in a 1. Then you're going to find the second derivative and then also plug in 1. So when you find the second derivative, you're going to start with the first derivative and again, take the derivative of each piece of the first derivative. This one's a little bit trickier than you would imagine on first pass. The first derivative is fine, but the second derivative is a little tricky. So just in case you can't see it, we have 2 to the x plus e to the x minus x to the 2/3 minus ln x plus 6. Okay, so I'm going to give you about 3 minutes to work through this and see what you can come up with, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's go through this. So our first step here is to find the first derivative of this function. So we're going to go term by term. The first term is an exponential term. So I'm going to use my exponential formula. So 2 to the x times the natural log of the base. So I get 2 to the x times ln 2 plus, now the derivative of e to the x is e to the x minus, now I have x to the 2/3. So that is a power function, which means I have a different rule. So here the 2/3 comes down and I subtract 1 from the power. So again, I have to recognize that this is not exponential and go back to my power rule from before. Minus, now the derivative of ln x is 1 over x plus the derivative of 0 or of 6 is going to be 0 because 6 is a constant. Okay, so again, you don't have to write the 0. If it helps you to remember that that's what the term went to, that's fine. It's completely up to you. So now we want to plug in a 1 everywhere we see an x. So here I'm going to have 2 to the 1 times ln 2 plus e to the 1 minus 2/3 times 1 to the negative 1/3 minus 1 over 1. So we need to figure out what can be simplified and what can't be simplified. So our first term here, I have 2 to the 1 times ln 2. The ln cannot be simplified. However, 2 to the 1 is just 2. So I can write the first term as 2 ln 2. E to the 1 cannot be simplified. So we'll just leave it as e to the 1. We don't want to turn to a decimal because then that will become an approximation. Here, 1 to the negative 1/3 is just going to be 1. So this is minus 2/3, and then 1 over 1 is 1. So we have two constants here. We have minus 2/3 and minus 1. So we can put those together and write this as minus 5/3. Right? They're both negative. We would turn the 1 into 3/3. And so this is what our f prime of 1 would look like if we didn't simplify any term that would make it not exact. Okay? So from there, we now want to find the second derivative. In order to find the second derivative, we need to go back to the first derivative. Now, this is a little bit tricky. So I'm going to trace over this ln 2 with red. We're going to follow that ln 2. That ln 2 is a constant. Our constant multiple rule says that your constant, right, so this is the same as this one, is going to multiply the derivative of the function. The derivative of 2 to the x is 2 to the x times ln 2. So we end up with 2 ln 2 terms, okay? Plus the derivative of e to the x, e to the x. Now here, I gotta be really careful with my fractions here. So my negative 1/3 is gonna come down to multiply the minus 2/3. The negatives will cancel. So I'll get plus 2/9 x to the negative 4/3. And then my 1 over x. So I want you to remember that we can rewrite this as x to the negative 1, right? We have to bring that x out of the denominator. So when we take the derivative, the negative 1 comes down and cancels the minus. So I get plus x to the negative 2, okay? So this derivative is not easy, right? We have to practice and we have to be careful with every single term that we don't lose anything. And so now we want to plug in a 1. So I have the natural log of 2 times 2 to the 1 times the natural log of 2 plus e to the 1 plus 2/9 1 to the negative 4/3 plus 1 to the negative 2. So how would we write this? How might we simplify this? Okay, so if we were to put this on a mini quiz or something like that, the most common way you would see this written, so 2 to the 1 is 2. And then we have 2 ln2s. So you have ln of 2 squared, because there's 2 of them, right? This one and this one. Plus e to the 1, right? We can't simplify that. But then here, 1 to the negative 4/3 is 1, right? 1 to any power is 1, times 2/9. And then 1 to the negative 2 is 1. So we have 1 plus 2/9 as our constant. And you can double check that on your calculator if you're sort of uncomfortable with this algebra. Just plug it in and you'll see that 1 to the negative 4/3 is just 1, right? So 2/9 plus 1 is going to give me 11/9. So this is sort of the simplified way that we would write the exact answer without turning any of our irrational terms into approximations. Okay, so hopefully that sort of makes sense as we walk through it so you can get some practice in plugging in values. Okay, the next thing that we want to do with our exponential terms and our logarithm terms is something that we sort of mapped out the process for last time. And so for the next 2 examples, we'll do them sort of together. Well, you'll try them, but we'll do them at the same time, right? Is we want to find the equation of the tangent line for functions now that include exponentials or logarithmic functions. So for the first one, we're trying to find the equation of the tangent line for f of x equals 2e to the x at x equals 0. And for the second one, we're looking for the equation of the tangent line to 3 times ln x at x equals 1. So as a brief reminder, in order to get the equation of the tangent line, which should be in the form y equals mx plus b, you need a point and you need a slope. The slope comes from the derivative and plugging in the x value. So that's why we're practicing these with the derivatives of these types of functions. And the point we get by using the x value into the original function to get the corresponding y value, which gives us the 1 point where the tangent line touches the function, and it's the 1 point that is shared. Once we have the slope and the point, we can put it together in y equals mx plus b. So I want you to take about 4 minutes and try out these 2. See if you can find the equation of the tangent line for each of them, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's look at the first one. So again, we need the point and the slope. It doesn't matter which one you compute first. So in order to get our point, we're going to take our 0 and we're going to plug it into the original function. Okay, so we have f of 0 equals 2e to the 0. E to the 0 is going to equal 1 because anything to the 0 power is going to equal 1. And 1 times 2 is 2. So when x equals 0, y equals 2. So that's our point. That's the point where the tangent line touches, and that's the point that's shared by the function and the tangent line. Now, to get our slope, we need the derivative. So if we take the derivative of 2 times e to the x, the 2 is a constant multiple, and the derivative of e to the x is e to the x. Once we have our derivative, we want to plug in the specific x value that we're interested in. So we're interested in what's happening at 0. So we have 2 times e to the 0. Again, e to the 0 is 1. So that gives me a slope of 2. Okay, so m equals 2. So when I think about the equation of my line, y equals mx plus b, I have y equals 2x plus b because the derivative tells me my slope. Okay, so now I need to solve for b. I solve for b by plugging in my point. So I have 2 equals 2 times 0 plus b. 2 times 0 is 0. So that tells me that b equals 2. Okay, so that means that my final equation of the line is going to be 2x plus 2. Okay, so again, I need a point, I need a slope, and then I'm going to put that all together. For the second one, I'm going to do the same process. So here, I have the function 3 ln x, and I want to know about x equals 1. So I'm going to start by finding my y value. Okay, so I have 3 times the natural log of 1. The natural log of 1 equals 0, and 0 times 3 is 0. So I have the point 1, 0 as part of my tangent line. Okay, so now I'm going to need to find the derivative in order to get the slope of the line. Right. So here, when I take the derivative of 3 ln x, the 3 is going to multiply the derivative of the function. So I have 3 times 1 over x. Now again, I want to plug in the value I'm interested in. So I'm interested in what's happening at x equals 1. So I have 3 times 1 over 1. 1 over 1 is 1 times 3 gives me a slope of 3. So now I have y equals 3x plus b. Again, the 3 came from the derivative. I need to solve for b. So I come back over here to my point. Y is 0, x is 1. So here I have 3 times 1. I'm going to bring that to the other side. And I get b equals -3. So the equation of my tangent line is 3x minus 3. Okay, so again, I need my point, I need my slope. What's going to change from problem to problem is the function that we're working on. And as we learn more derivatives, we can try different things here. But the process is still the same. And again, the answer should always be in the form of a line because we're looking for the tangent line, right? We shouldn't have x squareds in here or anything. It's always y equals mx plus b. Okay, so that's our tangent line. Now we're going to do an application. that has to do with some money type problems. If you're going to be taking Math 128, this type of problem will be particularly helpful because you will do quite a bit of work with present and future value. But I'm going to read the problem and explain a few things, and then I'm going to have you work on some of the parts, but we'll do them kind of in a very specific breakdown. So when your money is invested, it gains value depending on a lot of different things, right? One of the important things about it is how the money is compounded. And so we talk about what compounding means, and here it says it's the interest added to the principal, right? So the principal is the amount that you put in, and the interest is how much money you make on it, okay? If the interest is added once a year, so once a year they look at how much money you have in your account and they drop in a bunch of interest, they say that that's compounded annually. So annually means once a year. So if that's the case, then the equation that we use for annual compounding looks like this. FV equals PV 1 plus R to the T. So FV stands for future value. So that's how much you have at the end of your investment. PV is present value. So the PV is over here. So that's how much you start with, the amount that you deposit into the account. R is the interest rate that you're going to earn on your money, and T is time. So in this setup for this function here, T is your independent variable and future value is your dependent variable, okay? So we're going to start with two questions where we don't yet need to think about the derivatives. This is just getting comfortable with the equations. So for part A, it says, suppose you invest $1,000 into an account, so 1,000 is your present value, that has an interest rate of 2.5%. So that's R, but we can't use this as a percentage. We'd have to convert it to a decimal first. Then the question is, how much money will be in the account in 5 years? So we need to plug in 1,000 for present value, 0.025 for R, and time equals 5. Okay, so you're going to do that in a minute. But then we want to also compare that to what's called monthly compounding. So monthly compounding means that you are receiving interest every single month. Okay. However, you do not receive the full interest rate every month. You don't get 2.5% every single month. Instead, that 2.5% is divided up by 12, and you get 1/12 of the 2.5% every month, right? So you still have an annual rate of 2.5%, but now you're getting some of that interest each month. So the way that that factors into the equation is that future value is present value 1 plus R divided by 12. So now we're getting 1/12, but now we're getting it more often, right? So 12 times T. So 12 times a year times the number of years. So assuming the same numbers as part A, so the 1,000 present value, the interest rate of 2.5%, we want to calculate the future value if we are compounding monthly. And before you calculate part B, I want you to guess if you think that that's going to give you more money than part A, less money than part A, or the same amount of money as part A. So I want you to take about 3 minutes and try plugging these numbers into the first equation for part A and into the second equation for part B. Okay, so take about 3 minutes, then we'll go through that together, and then we'll look at part C and D of this problem. Okay, take about 30 more seconds. All right. So for part A, with annual compounding, our 1,000 goes in for present value, 0.025 goes in for the rate because I converted the percentage to a decimal, and we were talking about time equals 5 years. If I put all of those numbers into my calculator, I am going to get $1,131.41. Since we're talking about money, we use 2 decimal places, okay? So my $1,000 investment, right, over 5 years has grown to $1,131.41. If we compare that now to our monthly compounding, the way we set this up, we have 1,000 times 1 plus 0.025 divided by 12, because we're getting 1/12 of the interest each month, raised to the 12 times 5. So we get interest 60 times total, right? 12 times a year for 5 years. If I were to do that, I would end up with $1,168.93. So it turns out that if I compound monthly, I get more of a return on my initial investment. Why is that? Well, because you earn interest on the interest, right? So if you get 1/12 of the interest in January in month 1, you then make money on that interest that was deposited rather than having to wait until a later time. So what does that mean, right? When you are thinking about investing money and putting away money into a checking or savings account, if you have the option of an annual rate at one bank versus a monthly compounded rate at another bank, if the rate is the same, you want monthly compounding, okay? It may not seem like a huge difference, right? $37 over 5 years, but imagine that you have $10,000 or $100,000, right? As you are later in your life, that does make a really big difference. So compounding is pretty important. Now, you can see that both the annual, right, and the monthly compounding are both exponential functions. They both have that t up in the power. So for part C and D, for part C, we want for each of these formulas to find a function that represents the rate at which the future value is changing, keeping in mind that t is your independent variable and that PV and R are constants. So what does that mean? So that means we are looking for the derivative of each of these functions, right? So the original function, which is up here, and this monthly compounding function. So you need to think about what we're going to do with each of these letters. Again, that t is our variable and that R and PV are constants. How does that impact the derivative, right? And then for the second one that we have to do down here, this one's a little more complicated. So this one, we have to do some algebra on it in order to even take the derivative, similar to the algebra we did when we did e to the cx earlier today, okay? So you're going to try to get the derivative of both functions, and then part D, calculate the rate at which each function is changing at time t equals 5 if present value is 1,000 and the rate is 0.025. So we're trying to determine the rate of change for each of these versions. How quickly is our money increasing? Okay, so I'm going to give you about 5 minutes. See if you can come up with the derivatives, right? So again, this is really putting everything to the test, making sure we understand things like what is a variable, what is not, how do we apply the exponential derivatives, but give it a try, see what you can figure out, and then we'll go through it together. All right, take about 30 more seconds. All right. So our first equation that we're interested in, we had present value times 1 plus r to the t. That was our annual compounding. Here, the PV is a constant multiple, which means that the PV is going to multiply our derivative. So we have PV times the derivative of 1 plus r to the t. Since t is in the power, it's exponential. And so we get the same thing back, 1 plus r to the t times the natural log of the base. Well, the entire 1 plus r is raised to the t, so the base here is 1 plus r. So this is how we would write this first derivative, right, for the annual compounding. For our monthly compounding, it's a little more tricky. So we start with PV times 1 plus r divided by 12, all raised to the 12t. Well, remember, in order to have an exponential function and to use this rule, we need to have something just raised to the variable. So the first step is to rewrite this by separating the 12 and the t. And again, we can do this by just having the 12 with the 1 plus r divided by 12, and then raising that whole thing to the t. So what that means is that this part in the brackets, including to the 12th power, is the base now. That's the base raised to t. So again, the PV is a constant multiple times the original function, so 1 plus r over 12, 12 to the t, times the natural log of the base. So here we had to separate these so we could figure out exactly what the base is in order to include it correctly in this natural log term. Okay, so this is a little bit tricky on the algebra, right? But we can figure it out. And then for part D, we wanted to then apply the fact that time equals 5, present value is 1,000, the rate is 0.25 to see how quickly it's changing, right? We're calculating the rate with these values. So we have to plug them into these formulas we found. And then a secondary challenge, we have to plug these into our calculators really carefully. So we know that monthly compounding is better. So we suspect that the rate at which we're changing is probably going to be a little bit bigger for number 2. So when I plug these into my calculator, I got 27.94 if I round to 1 decimal place. And for the second one, I get 0.295. So when I round, I get 0.30. So what are the units on this? Right? So we're talking about money. And so this is $27.94 per year, right? Because the independent variable was time. And so we do the dependent units over the independent units. The dependent units are dollars. And this is $28.30 per year. So my investment is increasing by $27.94 per year with annual compounding, and it's increasing by $28.30 per year with monthly compounding. So it's increasing at a higher rate when I'm compounding more quickly. Okay, so there's a lot of algebra, derivatives, all these things sort of put together in a context, and hopefully you can see why we might need to know these derivatives to talk about analysis in business. This is just one example of many. Okay, so that's our last example for today. So we'll stop here. On Tuesday of next week, we're going to be doing the chain rule, which has a lot of algebra in it. So again, if the algebra has been shaky for you, please make sure to stop by drop-in hours anytime to get help on any of the algebraic stuff that may be tripping you up.